Today we're solving the train problem on Codewars. So given a train track with some trains on it, the same train track after some time passed, return true if the arrangement is valid, otherwise return false. So we've got these little caret guys who can, the angle brace who can represent a train, and then we've got the dots, which are like the empty tracks, and the train can move in the direction that it's facing. So this is valid. And then so these are trains traveling right, trains traveling left, and a space, a stretch of empty track. So you can't flip direction, you can't go backward, you cannot change length in the track. You can't create or destroy tracks or add or remove trains, and then trains can't go past one another. And then the solution should work for strings up to 30k characters. Doesn't really matter, but this is 3 trains in their theory. Okay, so we're going to get a pair of strings, and we're going to try to check whether or not they meet all of these criteria. So just sort of listing the criteria here. Before and after have the same length. The trains appear in the same order. As we scan through the string, we have to see all of the sort of forward and backward in the same order as before. So they might have moved, but we basically have to if they have I'm not doing a very good job of explaining this example here. The trains can move in their whatever the forward direction is for them, but they can't suddenly reorder themselves. So maybe another way to think of it is like the strings with the dots removed are equal. Now that doesn't fully specify the answers, because if we had in the first string we had this, and then the second string we had this, they'd be equal with the dots removed and they're the same length, but this isn't valid because we encounter, we've like moved backwards. We've seen more dots before the first string than the second string in the same spot, and so that doesn't work. So we have to sort of check each of these conditions. So this is condition 1. This is condition 2, and then this is condition 3. Trains can only move forward. This condition 2, trains appear in the same order. I think it's capturing a few of the different things. So trains cannot change direction. The track cannot change length, not created or destroyed, and they can't enter or leave a given section of the track, and can't go past one another. So there's a bunch of things that are captured in this rule too, and then we've got to figure out how we're going to implement each of these. So I'm just gonna basically early return out of each of these if it's not true. So if the length of before does not equal the length of after, we're going to return false. They have to appear in the same order. So if, so we're going to say if, how do we're going to replace, so we're going to before replace this with the empty string, and then we're going to replace this with the empty string, and then we're going to do that same replace operation to the after, and if those are equal, well, if those are not equal, we're going to return false. Return false. This next piece is a little bit trickier. Trains can only move forward. Let me just take a second to think about how we're going to solve this. As I'm doing that, let's just return true at the end if we've made it through these things and run the test and see which ones we're passing and failing. So we're passing at least some of them. Trains may not change direction. Interesting that we're missing. Oh, I've done the replacement wrong. We want to keep the angle brace. We want to replace all of the dots. We want to replace all of the dots. What am I thinking? Keep all of the trains. we want to remove the tracks. Let's try that. Oh, I've removed our colon here. Okay, so track can be empty. A single train can go right, left. Multiple trains can travel at different speeds. Trains may not go backwards. Okay, so this is the rule that we're missing here. And so just looking at these tests, we've got a couple of tests here that describe what we're trying to accomplish. Yeah, this is not, we're not allowed to do this. We can't start at the end and then move backwards to the beginning, or start at the left end and then move backwards. And then, yeah, this is the same idea. Just trying to think about what does it mean for a train to move forward or backward, just in terms of these strings. If we're counting up the dots before each of these trains, we have to have more dots in the, or more or equal dots before the train in the before string and the after string. So I think we're going to have to do some counting here. The tricky thing here is that we've got trains going in both directions. So let's just sort of focus on the forward direction first, and then we can reverse it for the other direction. So if we're just thinking here, the reason this is invalid is we've got 5 dots before the character this way, and then it's 0 dots before the character this way. And what we need is for there to be more dots before trains in the first string than after the string. Now, I think this is true sort of for each of our like forward arrows and for each of our backward arrows. So we'll end up here. We have to generate basically a list of the counts. So this one has is in position, well, maybe I'm thinking of this wrong. Maybe we just need to think about positions. Why bother with counting dots? We know the indices of the characters. So we can just say for each of the indexes as we scan from left to right, are each of the indexes of the forward arrows greater than they were previously? Let's do that. Let's say forward arrow indexes is a list. We'll go for character in our before string. We're going to say if the char is this, we need to enumerate before string because we need the I in the character. Word indexes append I. Let's print this and just see if I'm getting the logic right. I can't type this morning, so there's a good chance that I can't do the Python right either. Okay, go backward. So we should see 5 and then, go backward. Okay, so we're seeing this 5 we're enumerating before. And then in the second one, we're enumerating this before, and there's no forward indices. Okay. Let's just pull this out into a method. Find indices for some string and the character. This is a target character. We do this. We do this whole thing. Indices, I can pluralize properly. String, if the character is the target, then indices append, and then we return the indices. And then here we can say we've got the forward arrow indices are equal to the find indices of the before string and this target. So let's go the before forward arrow indices and then the after forward arrow indices. And then let's print these both. Okay. Okay. Okay, so before, after, before, after, before, after, before, after. Great, okay. So we've I think successfully found the indices of these things, and now we have to check that for each pair of indices, the before is lower than the after. So we're gonna basically step through each of these arrays and say, like, let's check them pairwise. So the 1 and the 0 and the 2 and the 6. There's a few ways to do this. We can enumerate again, so we can for I and then the index and enumerate the b forward arrow indexes. The naming is not helping me here. Then we would have to check if the a forward arrow indexes of that I is if we've moved backwards. So if the a forward is less than the index from the backwards direction. So if we've got this situation here where this is a 5 and then this is a 0, then the 0 is less than the 5. That's a situation where we have to return false. So let's run this test. We should get at least a different failure from before. Cool, yeah, we've passed the first test from this one. Now we're only looking at the forward arrow indices here. We have to do this in reverse for the backwards situation. Before back, after back. I'm not gonna mess myself up with all of the with the naming again. So we're gonna look at the backwards arrow. We're looking at the backwards arrow of the after string, and then we're going to do the same loop again, and we're going to loop through before back, and we're going to compare against after back. Okay, we have to actually reverse the direction of this too. So in the backwards case, we we need them to be, they must be the other way. So if we've moved, let's see, go backwards. Let's print these out just to see what the thing is. Before back, after back. Let's fail it again just so that I can show what that issue was. So in this go backwards test for this one, our backwards arrows start at 0 and then end at 5, and the direction of this is actually important. It needs to be reversed. I don't think I'm explaining that very well either. Yeah. Don't need this print statement. So we've got all of these tests passed, and we can click attempt just to see if we're passing the more. There's probably additional tests, and then we can take a look at the performance of this and refactor. So first, let's check the forward facing trains. The trains appear in the same order. That test is pretty clear. Before and after have the same length, so that test is also pretty clear. The naming here is not very good. Let's see if we can replace in both places using this editor. Let's call this before forward and after forward. If you haven't seen that before, you can hit like Control D, and that, or I guess it's Meta D, so I've got Command D, but it might be Alt D or Option D on a Windows. And you can select all instances of the text that match the same string. So if I've got this selected, it'll select the next spot that I've got that. The other thing that is just, it's possible, I think I'm gonna leave this solution as it is. This pattern of enumerating through and sort of comparing two lists in each place, this is also available through iter-tools as zip. It like takes two iterate pairwise. Zip takes two arrays and returns a like an iterator through the like pairs of that array. So if you've got A, B, C, and D, E, F, then zip of these gives you back A, B, sorry, not A, B, A, D, B, E, C, F. So zip is very, very helpful in exactly this kind of situation. I've done the like enumeration and like matching the indices up by hand, but that's a refactor that could, in theory, make this a little bit just tidier. Yeah. I'm not gonna bother with it. If you are really curious to see what the like one-liner version of this like 5 or 6 lines actually looks like, then ping me and maybe I'll record that video. But otherwise, so this was sort of a fun logic puzzle, just thinking through like how you actually implement these rules from the instructions. Let's just check that the refactor has actually worked. It looks like it has. Just a quick note about the runtime of this. The performance of this is going to depend on the lengths of these strings. So checking the length, Python's probably optimized this, but in general, it's going to be O of n in the length of the string. Replace, this operation has to walk through every character in the string, and so the performance is going to again be O of n in the length of the string. So just like talking about performance, perf, we've got 1 is O of n. This is like the length check. It's likely Python optimizes that length check a little bit, but we don't really know that for sure. Replace is similarly an O of n operation, and then so is the string equality. So this is actually like 3 O of n operations. But remember, if you sum up O of n, it doesn't. You can ignore those the linear terms. So this is all still effectively just O of n. And then step 3, just thinking about like what these things have to do. Find indices has to walk through the length of the string, so that's O of n. Find indices again. Enumerating through these lists of indices. The lists of indices themselves must be less than the length of the string, but they're upper bounded by the length of the string, and so this enumeration is again O of n. So we've got 3 O of n operations here, and then another 3 here. And so if you're just thinking about like how fast is this, we have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 n operations, where n is the length of the like before string. But if you're thinking just in big O terms, it's all just it's just linear. It's just O of n. If you're trying to speed things up, reducing that 11 down to fewer loops can be pretty significant. You could get, if you manage to do this all in one loop, you'll sort of look at each character and find all of the information you need. Then you'd certainly be faster. You could be up to 11 times faster, but you're not going to change the shape of this curve, the big O performance of this algorithm. Cool. That was maybe an interesting little diversion. Let's just after adding these comments, hopefully we don't mess up our answer too much, and then I'll submit. All right. Thanks for tuning in. Hope you enjoyed solving this strain arrangement problem. If we look at the solutions, we can see that yes, people are doing this zipping of before and after, and doing some checking, sort of the similar solutions to mine. Thanks. Bye.